All right, welcome everyone. So imagine you're trying to figure out what a whole country thinks about something. If you just sample people randomly, you might accidentally miss out on a key group, and your results? Well, they'd be skewed. Stratified sampling is the statistician's answer to this. It's a precision tool that helps us get way more reliable results. Okay, let's dive in and see exactly how it's done.
Here's our roadmap for today. First, we'll tackle the why, the basic logic behind stratification. Then we'll get into the nitty-gritty, the core formulas you need to estimate totals and means. After that, we'll figure out how to measure our confidence in those estimates, and then we'll look at the special case of proportions. We'll see it all come to life with a real-world study, and finally, we'll look at the whole thing through the super intuitive lens of sampling weights. By the end, you're going to have a rock-solid grasp of this technique.
Okay, first things first, before we even think about touching a formula, we have to understand the core idea. What is stratified sampling, and maybe more importantly, why is it so darn useful? Let's break it down.
Really, at its heart, stratified sampling is a divide-and-conquer strategy. Think about it like this. You've got a giant, messy pile of laundry. Instead of just grabbing a random handful of clothes, what if you first sorted it into piles: shirts, pants, socks? Then you took a few items from each of those piles. That's exactly what we're doing here. We take a diverse population, divide it into these more uniform subgroups that we call strata, and then we do a simple random sample inside each one. This makes sure we get a sample that truly represents the entire population.
Now, before we go any further, let's learn the lingo. Think of this as our cast of characters. H is just how many strata, or groups, we've made. Capital N sub H is the total number of people in a single group H. Add all those up, and you get capital N, the total population. On the flip side, little n sub H is the size of our sample from that one group. And when you sum all of those up, you get little n, our total sample size. Getting these down is going to make the formulas we're about to see make a whole lot more sense.
So we've split our population up and we've taken our samples. Now what? How do we take that carefully collected data and say something meaningful about the entire population? That's what we're going to figure out right now.
This is really where the magic happens. We've only talked to a small group of people, but we want to make claims about everybody. How do we make that leap? How do we use our sample to make a really good, unbiased guess about the whole shebang? Let's find out.
Okay, this slide is the absolute engine room of our analysis, so let's walk through it. Look at that first row. We start inside just one stratum, H, and we calculate its sample mean y bar sub H. That's just a simple average of the values from our sample in that group. Easy enough. Now for the second row, to estimate the total for that whole stratum, t hat sub H, we just scale it up. We take our sample mean and multiply it by the stratum's total population size, n sub H. We're essentially inflating our sample to represent its whole group. Then, for the third row, getting the population total, t hat strat, is simple. We just add up all the estimated totals from each individual stratum. And finally, to get the overall population mean, y bar strat, we take that big population total we just found and divide it by the total population, capital N. See that beautiful logical flow? We build it up piece by piece.
And this right here is a really important point. The final mean isn't just a simple average of all the stratum means. If you look at that last formula, you can see it's a weighted average. Each group's mean, y bar sub H, is multiplied by its share of the total population. That's that n sub H over n part. This is what makes the whole thing work. It means that bigger, more important groups have a bigger say in the final estimate, which is exactly what we want for an accurate picture.
And here is the best part. We can trust these estimators. Why? Because they are unbiased. Now, what does that actually mean? Well, think of it like throwing darts. An unbiased thrower might not hit the bullseye every single time, but on average, their throws are centered right on it. There's no systematic error pulling them to the left or right. It's the same with our estimators. Any one estimate might be a little high or a little low, but on average, they hit the true population value. That gives us a ton of confidence in our method.
So we have our estimate, a single number. But any good statistician will ask, yeah, but how sure are you? Just giving a single number is like guessing the temperature. It's helpful, but a range would be better. So in this next part, we're going to learn how to calculate a range of plausible values for our estimate.
You know, this is one of the most elegant parts of stratified sampling. Because we sampled independently within each group, the math to figure out the overall uncertainty, the variance, becomes incredibly simple. The variability from one group doesn't affect the others, so we just figure out the variance for each stratum's estimate and add them up. It's a really neat property that makes our lives a whole lot easier.
All right, let's break these formulas down. They might look a bit intimidating, but every piece has a job. Let's focus on that top one, the variance of the total. That first bit, 1 minus NH over NH, that's our finite population correction, or FPC. It's an adjustment because when we sample without putting people back, we're reducing our uncertainty a tiny bit with each pick. The NH squared term, that scales the variance up because we're estimating a total. Since variance is in squared units, our scaling factor has to be squared too. And the last bit, SH squared over NH, that should look familiar. It's just the basic variance of a sample mean. So we just do that for each stratum and add them up. The formula for the means variance right below it is basically the same, but it's scaled by the squared population weights, which properly adjusts it for the mean.
Okay, now that we have our variance, we can finally build a confidence interval. Think of it like a fishing net. We cast this net and we are, say, 95% confident that the true population mean is caught somewhere inside it. It means if we did this whole process 100 times, our net would capture the true value in about 95 of those tries. And to build it, we just take our estimate, calculate the standard error, which is just the square root of that variance we just talked about, and then add and subtract a margin of error.
All right, let's switch gears and look at something that comes up all the time: estimating proportions. What happens when our data isn't a continuous number like income, but a simple yes or no answer? Well, it turns out our formulas adapt beautifully.
This is such a neat trick. When you're dealing with binary data, yes or no, true or false, you can code one answer as a 1 and the other as a 0. And if you do that, the mean of all those 1s and 0s is, by definition, the proportion of yes answers. It's a fantastic insight because it means we can use all the formulas we just learned for means and apply them directly to proportions. We don't have to learn a whole new system.
And you can see it right here. These formulas are practically twins of the ones we just mastered. The estimated proportion, p hat star, is just a weighted average of the sample proportions from each group. And look at the variance formula. It has the exact same structure as before. We've just swapped out the sample variance term, s squared, with the specific variance formula for a proportion, which is p hat times 1 minus p hat. It's a perfect example of how the same core statistical ideas work for different kinds of data.
We've gone through a lot of theory, so let's make this real. We're going to look at a study from the American Council of Learned Societies. They use this exact technique to learn about their members. This is where the rubber meets the road.
So here's our data. On the left, those are our 7 strata, the different academic fields. That membership column, that's our capital N sub h, the population size for each group. Sampled is our little n sub h, our sample size. And that last column is the sample proportion of female members they found in each discipline. That's our p hat sub h. We have every single piece we need to solve this puzzle. Okay, so here's our mission. Use this data to estimate the overall proportion, and then the total number of female members across that entire population of 44,000 people. Let's do it.
After we plug all those numbers into our weighted average formula, we get our estimate, 24.65%. Now this is really important. If you just took a simple average of the percentages in that last column of the table, you'd get a totally different and wrong answer. Our calculation correctly gives more weight to the bigger disciplines like history and literature, and that's what gives us the accurate final number.
And once we have that proportion, getting the total number is a piece of cake. We just multiply our proportion, 0.2465, by the total population of 44,000. And that gives us our estimate, about 10,847 female members in total. See how those formulas just lead us straight to the answer?
We've been dealing with some formulas that can look a little abstract, but what if I told you there's a much more intuitive way to think about all of this? For our last section, let's explore sampling weights, which can really make this whole process click.
So a sampling weight answers a really simple question. How many people out there in the population does this one person in my sample speak for? And the formula is as simple as it gets, just the population size of the group divided by the sample size from that group. It's a way to correct for any over- or undersampling we might have done.
This example makes it crystal clear. Let's say our population has 1,600 men and 400 women, and we sample 200 of each. For the men, the weight is 1,600 divided by 200, so it's 8. Every man in our sample represents 8 men in the population. But for women, the weight is 400 divided by 200, which is just 2. Each woman represents only 2 women. Why are they different? Because we intentionally oversampled the women relative to their population size, and these weights perfectly correct for that imbalance.
And when we look at our formulas to this new lens of weights, they become incredibly simple. To get the estimated population total, you just go through every single person in your sample, take their value, multiply it by their own personal weight, and then just add it all up.
It's a much more direct way to think about it, and it gets you to the exact same answer.
So we figured out how to analyze a stratified sample after we have one. But that brings up a huge question, right? How do we decide how many people to sample from each group in the first place to be as efficient as possible? Should we sample proportionally, or should we take more from groups that are more varied? Well, that is the art and science of sample allocation. And that's a fascinating story for our next explainer. Thanks for joining me on this deep dive.